the same way. It's so long to see you guys from Thursday, Friday, Saturday, Sunday, and then next time, Monday also. I mean, it's going to go so long without seeing you guys. So, all right. I'm sure you guys aren't too sad. Who'd like to start us off with a prayer? Thank you, Isaiah. Amen. Thank you. Let's start off with comments about the devotional from yesterday with Elder Tashira. Yes, Christine.
It goes to show how, like, when you're pursuing kind of like anything in life, including spiritual goals, but also with other things that are hard, it's better to like stick with it and to just keep making whatever effort that you can to do those things instead of just being like, oh, I'm not good at it right now, so I guess I might as well just drop it. And I also like that he said that like God is mindful of you and what you need because I think it's important to remember that something is easily forgotten.
Yeah, fantastic. Thank you very much. Yeah, the keep pedaling analogy is just fantastic. And as I was reflecting on it, I thought of people who I know that some of them have gone on missions and they came home and they stopped pedaling. And now some of them are less active. Some of them want nothing to do with the church and they've just gone downhill. I can't remember if I shared this in this class or not, but I have a good friend. His son was working at a fast food restaurant with a return missionary that had gone anti. And the return missionary worked on this kid every day, trying to get him to give up on the church. And the young kid, I mean, he was faithful. Dad's awesome. Grew up in an awesome family. And he went home one day to told his dad, you know, all this kid has to see that he's wrong is to look how miserable he is. Like I just see how miserable, like he just lives a sad life and he's not happy at all. Why would I believe what this guy has to say? Like he's not happy. So it was very, very interesting from a kid who was well beyond his years. And that kid's probably back from his mission now, just about now. So served in Fiji. So yeah, just keep pedaling. Don't give up. You'll get through those hard times. Just keep pedaling. Fantastic lessons. Okay, any other last comments? One last comment on devotional? Okay. I didn't start the recording. Can you? Okay, thanks. Okay. There were quite a few theorems like this in section 3.2, a lot of properties of operations. And we're not going to spend a lot of time on them. I'm going to hit a few highlights. So especially matrix multiplication. First, what isn't on there? Commutativity. Like these matrix multiplication doesn't commute in general. AB is not generally BA. There are some times when it does work, but in general it's not there, so we have to be careful. Scalars always commute. If you have a scalar times a vector, or a scalar times a matrix, you can swap the order on those. So when you do the left distributive and right distributive, notice that when you have A times quantity B plus C, the A has to stay to the left of B and stay to the left of C. If it started on to the left of A times quantity B plus C. And same thing with the right distributivity. If C's on the right here, then you've got C on the right. When you distribute it, it's got to stay on the right of the matrices on the inside. So, and the identity matrix down at the bottom, it always commutes. That's one situation where we do get commutativity. Um, you can, A times the identity matrix is the same as the identity matrix times A, always. Properties of the transpose. Most of these are pretty straightforward. It'll help you could convince yourself. I suggested in the reading notes that for each of these things, you pull out a matrix and try it out. Okay. The transpose of the transpose is you're back to the matrix because you're basically flipping the matrix and then you flip it back again. So makes sense. So most of those make sense except for D. D is not so obvious. You guys may have tried with some matrices. I hope you tried this out, but we're going to go through it also. Because this is the one that's like a little bit crazy. Why do you swap the order 2 when you distribute that transpose over multiplication? So here's a 2-by-2 proof. This is what the book would do. And it's really hard to follow because of all the sub things. So I changed it up to use 1, 2, 3, 4, and A, B, C, D. It's a lot easier to follow than paying attention to with subscripts. Here, my 1, 2, 3, 4, I'm not using them as those numbers. I'm just using them as placeholders for whatever might be there. So, so I just start following. To do this proof, I just start with the left-hand side and just start doing the operations to get it to look on like the right-hand side. So I pick an A and a B, an arbitrary A and a B. This only works. Proof is only valid for the 2-by-2 case. But then I look at A, B transpose. I multiply A and B inside to get that matrix. Then I transpose it. And then the hard part is seeing like, how can I rewrite that one? How can I rewrite that this one here as a product? And you can see, I mean, it's not hard. I know what it should be, right? It should be B transpose A transpose. So, and you can see that I have AC times 1, 2 in this upper right-hand cell, AC 1, 2. And I have AC times 3, 4, AC 3, 4. And BD times 1, 2. And so I get the BD on the lower side, 1, 2, in that first column. And BD times 3, 4. So it works out, and ACBD is the transpose of B, and 1, 3, 2, 4 is the transpose of A. And I have to write them in that order for the multiplication to work out. So, questions on this? I know, boring proof by slide. Yes?
think it kind of relates to what you're doing with
3.2, the written homework? No, the web assign? Yeah. Okay. When we come to a break, let me take a look at that so we can see. Or Michelle, if you want to pull it up so I can quickly come over and see it. Okay. So the matrices don't have to be the same size. I did a 2x2 in both cases, but they don't have to be the size. They just have to be compatible with multiplication. So here I have a different A and a different B. And the question is, what size will AB transpose B? So think about that, work with your neighbor. Phil, did I get those right? Like that? Okay. So what size is AB transpose going to be? Anyone figure that out? What size is just AB going to be? Should be a 3 by 2. Right, because I have 1, 2 times AC, 1, 2 times BD, 3, 4 times AC, 3, 4 times BD, 5, 6 times AC, 5, 6 times BD. So I still have my 3 rows and I have my 2 columns. So it should be a 3 by 2. That's AB. I haven't transposed it yet. And then if I transpose, then I would have a 2, 3. If you think the naive thing, so if you think, well, AB transpose should be A transpose B transpose, now what size will A transpose B transpose be? I mean, sorry, what size, yeah. What will A transpose B transpose be? That's too many B's in that question. Sorry, what, Sydney? It's not defined. You can't even do that. And so this is one way to convince yourself that this is not, this isn't right. These kind of things are a great thing to do when you're on your homework trying to figure things out, when you're reading in the book and it does an abstract stuff. Pull out some specific values, pull out some specific matrices and start working through it to convince yourself. It's also a really good strategy on exams. You're going to have lots of things where you have to decide if they're true or not. Pull out some specifics. If you can't reason through the abstract, reason through the abstract is basically doing the proof. And I know, so when you struggle with that, at least pull out some specific matrices and start working through it and see if you can convince yourself if it's right or wrong, one way or the other. Yes, Philip. So the identity is up here. So AB transpose is B transpose, A transpose. The order is switched when you distribute that. And the reason one reason you can convince yourself you need to switch is to actually make it so it's actually possible to do that, to do this multiplication every time. So yeah. Yeah, and so if you actually write B transpose A transpose, you actually get a 2 by 3. So even though it still might not be the same 2 by 3, we did a proof for the 2 by 2 case. At least you get the right size, so you can start to convince yourself that makes sense. Okay, let me answer Philip's question. I know some others of you had this question too. So the question on the web sign said, it was a question about find A, B, C, and D so that this matrix commutes with these two things. So what does it mean to commute? It means that if I multiply AB times CD, if I multiply this matrix on this side, I get the same thing as multiplying the matrices, but one's on the left and the other one's on the right. So this needs to be true. And ABCD 0, 0, 0, 1 needs to be the same as 0, 0, 0, 1. ABCD. So for it to commute, these need to be the same. And with this, start doing the multiplication and you'll get a system of equations that you can start working with. So so you can multiply this out. What do we have? We get an A, 0, C, 0. So on the left, A, 0, C, 0. Did I do that right? Yeah. And then that has to be the same as A, B, 0, 0. Okay, so if those things have to be the same, what do we know? CS equals 0, BS equals 0. And then you can do the bottom one, see if you need, it might give you more information too. So, okay, does that help? Yeah. Yeah, this is a nice strategy when you're trying to find things that commute. This is a common question. That just set up an ABCD or wherever the unknowns are, and then start start solving the system of equations that will fit that. Okay. Okay, Philip, thanks for asking that. Okay, brief comment about proofs in linear algebra. There's two main kinds of proofs that we do. The one I just did is this first kind where you basically blow up your matrix and you look at all the entries in the matrix. That's what we did. I had an A, B, C, D, I had a 1, 2, 3, 4. To do that proof with general matrices, I'd have to do not just 2 by 2 for each one, but I could do this and write A is that, B is this. I've matched up the number of columns here is the same as the number of rows here, so I know I can multiply them so that n here and the n here, that makes sure I can do that. And then I can work through the same stuff, and I've got a bunch of ellipses, these dots to work with. That's one way to do these proofs. I was really comfortable doing proofs like that when I was in linear algebra. I mean, of the proofs that we had, I was more comfortable doing that. I could go down to the specific entries. The other kind is, and sometimes we have to do this, especially when we're proving basic properties. But once we have a handful of properties and theorems to work with, hopefully we don't have to go back to writing out each cell. And that's the kind of case that we have here. Come on. I wish these would go to the side. But that's the kind of case we have here. This is on the slides. If A is invertible, then the inverse of A is unique. So if you assume that B and C are two inverse matrices for A, well, if they're inverses, then you know B times A or A times B is the identity matrix. And you know A times C or C times A is the identity matrix. We'll talk more about inverses today. But, and then here's the proof, and you're just using properties of things that you already know about the matrices that you have, and you don't have to go down to specific matrices, and that's much shorter, right? We're using the power of the properties that we know and theorems that we have. So there's some proofs you can do either way, even if you try to do it the second way if possible. So try to challenge yourself to see, like, how could I do it this way? Yes. That's right. Yeah. So yeah, for inverses, we're getting there. But yeah, for inverses, these matrices have to be squared just to have a chance of having an inverse. That still doesn't guarantee it. But yeah, if A is invertible, then we automatically know it's square. And this assumes that A, B, and C are all the same size, so you can actually do the multiplication too. So very nice. Okay. All right. That was just a note for me. Some of you had questions, either from office hours or you asked me afterwards. When we ended last time, I had two transformations written up here. They were something like this, 2003. And this was a stretching transformation. 2 times in the x and 3 times in the y direction. This was a rotation 90 degrees to the left. And I said that we're doing this first and then we're doing this first. I'm sorry, this second. Doing this one and this one. And people are like, why? It's backwards. You've got this one and then this one. This is actually the transformation we do first if we're doing right multiplication. So our vector is over here. So when we multiply the first matrix we multiply by this vector is this one. So we do this transformation first, and then whatever we get from that, we multiply by this one. So this is the first transformation. This is the second transformation. So, sorry, I didn't mean to confuse you. I should have emphasized that last time. But it's because we're doing right multiplication. Right now, we're talking about transformations only in terms of right multiplication. So we read left to right. We do multiplication usually left to right. So it's easy to think like, oh, I do this and then I do this. Nope, this is the first transformation and then this. So, okay. Speaking of transformations, okay. Back to 7th grade. 2x equals 6. If we want to solve this, we can think about this as we have a vector. We don't know where it is. We don't know how big it is or which direction it points on the number line, but we stretch it by a factor of 2. This is a transformation. This is an unknown. This is the result. Okay? And I end up with that vector at 6. And my goal is to figure out what did I stretch by a factor of 2. Right? And of course, we already know what it is. But when we do this, when we do the process of solving, we multiply both sides by 1/2 or divide by 2, and you get 1/2 times 6, which is 3. And so what we did is, you can think about this as I'm doing the inverse operation to the vector that I know in this problem, and the vector that I know is where I ended up. And I'm going to start with the vector I ended up with and go back and shrink it by a factor of 2. Well, maybe stretch it by, shrink by a factor of 2, stretch by a factor of 1/2. Make it half the length, whichever way you want to say it, okay? And this is a lot easier to think about when you have complex, this is a nice solution strategy when you have really complex problems. Because here, you think, oh, I do something to this unknown and I end here, but you don't know where to start. So this transformation is kind of, this one's easy, but if you have a hard transformation, like where do I start so that I end up right there? Well, if you can figure out, if you know the inverse operation with this thing, then you start at where you ended up and do the inverse operation, and then you'll get this x where you needed to start. Okay, that's exactly what we do with our most popular equation in this class, ax equals b. Here we have a transformation. Here we have an unknown. This is an unknown vector or an unknown point. And under that transformation, we know we end up at this point. Okay? This is a fancy way of writing the system of equations we worked with in chapter 2. Here's the result. So how do we go about solving this? Yeah, this thinking is the same here. Well, I have some transformation. I do it to some point that I don't know what it is, and I know I end up with b. Well, if we think the same thing as here, say, hey, let's start with b, and let's do the inverse transformation of a, and we will know we will end up at x. So okay, so algebraically, you can see like, oh, I multiply this side by a inverse, and I multiply this side by a inverse. Ooh, I did a shrinking transformation on that a inverse. Let me do it over here. Ax equals B. I can multiply both sides on the left. I have to pay attention to what side I'm multiplying on. I'm not going to put an A inverse here and then an A inverse here. That's bad, okay? Those might not be the same thing. So A inverse on this side, A inverse on this side, okay? And then A inverse times A inverse is the identity matrix. And A inverse times B. And the identity times X is just X. So A inverse B. So same idea as the simple algebra here. Could I do it on the right side both times? That was the question. So if I have AX equals B, if I multiply on the right hand here, then I can't get this A and A inverse to cancel out, right? Because I need to commute to do that, and I'm not sure if that's going to always stay if I do the commuting. So I have to be careful there. So no, in general. Okay, I don't know who had their hand up first. We'll go with Isaiah and then Philip.
So this kind of relates to that, right? If you're not looking at the equation, just like the inverse commutative, like A times B inverse A equals
Yes. So that question is, does A and A inverse commute? Yes, A and A inverse does commute. So yeah, that is true. So okay, Philip, is that your question? Okay, great. Yeah, so the identity always commutes, and the matrix in its inverse, they always commute. Yes? Absolutely. So our question was, can we think about that identity matrix as a 1? Yes. So that's a lot like multiplying by a 1 in this situation. So it's not going to change it. So absolutely. Yeah, so the identity matrix is like our 1. And in the same way that a multiplicative inverse, m times 1 over m equals 1, in A times A inverse equals the identity matrix. So get those same things. So nice connection. Other questions? Yes. So in this class, when we think of transformations, we're always transforming a column vector on this side. So we're always dealing with right multiplication. So it's always the order of the transformations is always right to left. So you're welcome. You can't, like, you could put on a row matrix over here and do it. I haven't even thought about that, about how that works and if the transformations are even the same. But in this class, we only deal with transformations by multiplying on a column vector over here. Okay, good question. Okay. All right, let's do a specific example. Simple specific example. Okay, so here I have a simple matrix multiplied by xy, I get 4x. This is simple enough I can think about what the transformation is. Okay, so turn to your neighbor. We did a little of these last time. Let's see how well we are. Turn to your neighbor. What transformation would this do to a random vector in the plane? So talk to your neighbor for a second. And see if you can find the inverse of that matrix. What's the inverse of this matrix? All right. So if we think about this situation, this equation here as this matrix is going to do some transformation on a random vector and take it to force 6. And we want to know what this random vector is. My first question is, what is this transformation here? What does this matrix represent in terms of a transformation? Someone raise your hand and let us know. Yes, Madeline. Okay, so multiply x component by 2, multiply the y component by a -3. Okay, great. I already had the 2003 over there and had things written down, so hopefully it wasn't too bad, but we'll get better, especially when we dive into transformations, of connecting exactly what matrices do what transformations. Some are more complex than we'll look at in this class. But so what's the inverse of that? What is the inverse of this matrix? Someone have a guess? Rhett? Okay. Why did you say this why would you claim this would be the inverse? Yeah, so you used the formula that the book gave on how to find the inverse of a 2 by 2 matrix. Okay, so that's how you got this. Okay, so you used this a little on the WebAssign. So how do you find the inverse of a 2 by 2 matrix? There's a nice formula here. Later on, we'll learn how to do, next time we'll learn how to do 3 by 3s and 4 by 4s and other things. I wish there was a slicker formula for those. It's not. So, but at least there is one for 2 by 2s. Okay, so using the formula is one way to get this. Did someone get it another way? Yes. Okay, so you thought about the transformations, and well, if I'm doubling the vector in the x direction, I need to shrink it by a half to get it back. If I'm changing directions and going 3 times as far, I need to change directions and go 1/3 as far to get it back. Great. So either one of these, fantastic. This will be really nice because we can't always think about transformations for a random 2x2. So at least we can always go for this formula. We can test this out and actually check and see if this is the inverse of this. So we can multiply 1/2, 0, 0, minus 1/3, 2, 0, 0, minus 1/3. And what do we get? 1/2 times 2 is a 1 plus a 0. Then 1/2 times a 0, a -3 times a 0. 0 times a 2 is a 0, minus 1/3 times a 0. And 0 times a 0, a minus 1/3 times a -3, 1. So they are inverses. Okay. And inverses are unique. This is the only inverse, okay, of this matrix here. There's only one matrix we could multiply by and get this. Okay. And you can swap those if you want and do this one times this one. In the reverse order, you'll still get 1, 0, 0, 1. Okay. Any questions here? Okay. Okay, let me pull up our friend Bart really fast. Oh, darn it. Okay, so here's our friend Bart. We're going to transform him. I want to talk about this guy right here. Okay, this formula is called the determinant of the matrix. This formula only works for 2x2s. We have a whole section on determinants later on that we'll study them to find things 3x3s and such is harder. But what does that determinant represent? Well, if I do a transformation here, so let's do the one we had up there, 2, 0, 0, a -3. So we did some stretching. In the process of that stretching, the area of the picture changed. How much larger is the transformed picture than the picture we started with? Multiplicatively, how many of these initial ones would it take to fill up the one our transformed Bart? Okay, so 2, 0, 0, -3 makes Bart 6 times as large in area. Okay? Also, something else changed about Bart. What else changed about Bart other than the stretching and the area changing? Direction. It's called orientation. So he was looking, well, he's looking both to the right, but if you follow, oh, there's not a D in the corner, but if you followed A, B, D, C in the small picture, if that upper right hand up here was D, and we went A, B, D, C, then we were going in the counterclockwise direction. Here, if you do A, B, D, C, A, B, D, C on the new one, We're going clockwise. Something reversed. It's called the orientation reversed. Okay? So this reverses the orientation of Bart. Okay? This determinant, it tells us how the area changes in the transformation and if the orientation changes. So, so the absolute value, AD minus BC, that absolute value is the factor by which the area changes. And the sign of AD minus BC tells us if there's a change in orientation. Okay? And if it's negative, the orientation changes. So negative means change. Okay? If it's positive, it didn't change orientation. So let's get back to Bart. So I have this transformation that does some stretching. If I do the inverse transformation, the change in the area needs to be reduced by the same factor it increased, and the orientation has to change back, right? And that's what this determinant captures right here. So when I divide by AD minus BC, I shrink the area back down. Here, what is it in our case? What is AD minus BC? What's the determinant of this? It's a -6, right? So -6 minus 0, it's a -6. So when I divide by that, -6, I'm going to shrink that, I'm going to shrink by a factor of 6 the area, and that -1 means I'm going to change the orientation back. So this should make sense why we have this piece in the inverse formula, because I have to undo that growth or shrinkage and the orientation change if I have it. So that's what that's doing for us. Okay. All right. Okay, with your neighbor, come up with a matrix that has the determinant of 0. All right, someone have one? A 2x2 matrix as a determinant of 0? Okay, someone said 1, 1, 1, 1. Okay, you got another one? 1, 2, 1, 2. Anyone got another one? 1, 1, 2, 2. Okay, so someone got another one? Go ahead, in the back. Plaid face mask. 2, 4, 3, 6. Okay, all right, because you get the 12 minus 12. Very nice. James? 0, 1, 0, 1. Okay, you get 0 minus 0. All these, they work. Another one I'll throw up, 0, 0, 0, 0. Okay? What do you notice about all these? They're not all symmetrical. Okay. Yeah, someone said dependent. all of these have dependent rows and dependent columns. Okay? So, and what happens if we try to find the inverse matrix to one of these? Let's do our formula. So you get the, oh, I'm going to swap the 1 1s. This becomes negative, negative. So I did my formula, but then I have to divide by 0. Yeah, I mean, like, that's a problem, right? Okay. Well, what's going on? Let's try one of these on Bart. See what happens. So we'll just do that first one, 1 1 1 1. So 1 1. Is that already a 1? I'm going to move that around. Nope. 1. What do you think is going to happen? Tell your neighbor, what do you think is going to happen? He'll blow up and never come back? Dun 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 dun. What happened? He disappeared. Everything, every point on that plane, if you multiply it by 1 1 1 1, it gets mapped onto one line, the y equals x line. And what if you try to undo that mapping? That's what the inverse does. How do you undo that transformation? This transformation compresses everything down to one line on the plane. How do you undo that? You can't, because there's infinitely many points that have been pushed down to this B prime right here. And so I don't know where it goes. I don't know how to undo that. I don't know which of those infinitely many points that are sitting there. I don't know where to put them back out on that plane. So I'm toast. The same thing actually happens. I know you haven't thought about it this way, but the same thing actually happens when you multiply by 0 on the real number line. Because this transformation shrinks everything, every single value on the real number line, it shrinks it down to this point. And now you try to undo that transformation. You can't, they're all right there. You don't know which point came, you don't know how to undo that one point. That one point has to go to all possible points, and you can't do that. Same thing in this situation, except it smashes it down to a line. If you do this one, it takes the whole plane and compresses it down to one point also. So any of these other ones, this will compress it down to a line, that will compress it down to a point. But we lose a dimension, and once we lose that at least one dimension, we're toast and trying to find inverses. Yes, Philip.
So when we're multiplying a matrix by determinant matrix, you're saying it shrinks it down to one?
One shrinking it down. It's these transformations. So these shrink the plane to a line or a point. So these transformations, but these all have determinant equals 0, right? These all are determinant equals 0 matrices. So that's how we can find matrices that do that, and that's how we can find if a matrix has an inverse or not. Because if the determinant equals 0, then the inverse doesn't exist. And if the determinant doesn't equal 0, an inverse does exist. And it's equivalent to saying the determinant equals 0. It's equivalent to saying the columns of the matrix are linearly independent. I'm sorry, linearly dependent, and the rows are linearly dependent. So those are all equivalent. So, okay. Questions about this? All right. Have a great day. We'll see you next Tuesday, which is really a Monday. Homework's up over here. So Start studying for the exam, which is next week, starts next week.